Welcome everyone to another OCP Tab call. This is call number 132. Today we have Magnus Danielson. Magnus has been working at Net Insight since 1997. That's a lot of time, Magnus. As a
Yeah.
senior technologist, he works on synchronization and resilient standardization in ITU and IEEE. He's also part of the WSTS and the IFCS conference. He is an IEEE Senior Member, and today's talk is about PTN or ePTS for timing in wide area networks. So, with no further ado, Magnus, the floor is yours.
Thank you. So I should maybe explain the difference between PTN and ePTS. PTN is what we call it as a product, and then as we put it into standardization, that's in ITU we call it ePTS. So that's a starting point. And I've been working with synchronization essentially from the start when I started with NetInsight, and it has been an integrated part of our media product range. In addition to that, we have started to look on it for time distribution as a separate thing, and I think that is what we will focus on here. I just need to have the how do I change slide? Um, there. So I start off with, for those who don't know, some of the timing challenges we have in 5G TDD. Um, it's important to remember that in TDD, you have phase alignment and not only frequency as with many of the previous mobile networks. And the first thing you need to do is within the operator's own network, you can have a maximum of 3 microsecond error difference between any nearby antennas to avoid interference. And the way that this has been solved in the, the ITU-T standardization is to say that all stations should have their radio interfaces within 1.5 microsecond to the common UTC reference. And the common UTC reference is typically achieved through GPS GNSS receivers, which have been so easy to deploy. And when you can use that, it's a wonderful solution. But as we all know, the world do not allow simple good things. There is a second thing that you need to think about also, and that's the between network operators, you have also need the timing to be well done, because otherwise you end up with interference problems between the operators. And this is traditionally you separated things on frequency alone, and that's been sufficient. However, we've seen that frequency separation alone is not sufficient. You also need to have good timing of both of all neighbor operators in that same region, and it can be a little bit difficult to analyze when you don't have those, because you might not think about that as being a problem. Now, loss or lacking the ability to achieve timing creates interference. Um, and that can be one of several different problems. But the recurring thing is it can be hard to see and analyze if you don't know that you need to look for the synchronization. Um, I like to look on timing threats as operational challenges. Um, that you really need you need that common timing to be, I mean, regardless of what the situation is, losing your timing is a problem. So if GNSS is unavailable, you're indoors in tunnels, there could be cost of just installing an antenna. That could be a problem. There could be operational loss. You have broken equipment, you have a sapped antenna, unexpected blocking. We had too high water level in the antenna, snow on antenna, Christmas trees put on antenna and with snow on that, ice, whatever. There are a number of things that can fail. Then we have jamming, and that could be unintentional or intentional, but the purpose of that is blocking GNSS reception. And spoofing, that is sending out a false signal, intentional or unintentional, interesting enough. But regardless of which of these problems you have, they are a threat to your operation. So that's something you need to kind of always have. GNSS is a fine signal when it's there. When it's not, you need to have a solution for it. And because as it will become have operational consequences, and essentially it's about locally or within a region turning off the money machine for an operator. That's not popular. So securing access to synchronization is something that makes the system more robust. So let's look on the different ways of doing this. One way of saying, of course, is you can make your P2P grandmaster have holdover. And if you go for rubidium or cesium, that's kind of expensive route. It's possible. But the trouble is you only get into this or that many days of it's still a temporarily only solves temporal loss. Do not really solve unavailability. We even seen jamming situations that go on for years. So depending on where you are, it's actually do not really solve your problem. One approach that is kind of the base approach is that you have full timing support for P2P everywhere. And locally, that's typically fine. However, the topic is for the WAN, we have a problem that it's expensive to ensure that all equipment have functional FTS support. And when saying functional FCS, it's not only that it has FTS support, but it's also actually performing what you need. It's also prone to problems where it's too easy to insert non-compatible equipment, and it can be a little bit hard to locate depending on your skill set and the exact situation. You might not even have access to that part of the network because you might be renting a part of the link, for instance. Well, for this purpose, the operators put the requirement that there need to be a way to jump over the WAN part or over a network which is not supporting timing, and that's where the partial timing support came up. And the trouble with that is, well, it kind of works if you have a good enough network. Trouble is, many of the WAN networks is not meeting those requirements, and I will illustrate that in the next slide. So what we then been working on with our technology is addressing a number of these points, and I will go into the details of that further in the presentation. And this is that here you can start balance cost and performance. So we try to use what we call enhanced partial timing support to jump over the WAN, do a number of things that is needed. And this is the way to jump over the parts that do not have full timing support. But then you go over to a not full timing support island, and that's fine. So here's an example where we had a partial timing support link and an ePTS link. in parallel. They're jumping over the same link at the same time. And this is quite a typical network link which do not have timing support. And we could see, in this case, we were measuring 10 peaks of 10 to slightly more than 10, 11, 12 micros. And this is reoccurring. This is quite strong noise that the network is providing. And this is the situation where PTS is not able to deliver the 1.1 micro needed for mobile networks, because that's the handoff to the RAN part specification. And whereas the ePTS, with its filtering, etc., is able to push it down to 500 nano. And it illustrates that the situation that for some uses, for this link, let's say that you're doing financial tech and need to meet regulation for MiFID II or something similar. 100 micro is fine, and PTS is doing just perfectly for that. Good, but it's not meeting the requirements for the mobile network. So depending on what you're doing, depending on the so it's a little mixed situation. And one of the things we did, first of all, you need to do a nonlinear filtering. You need to do what's called locket packet filtering, minimum filtering. So we, rather than being 16 to 128 packets per second, we do 500 up to 20,000. We can do even more. And that's when the filtering is able to do something useful. Another thing we do is we actually adjust the packet MTU size. And from a P2P perspective, this is not something you would like to do, because when you're in your full timing support world, there's no benefit. Why add additional data? However, when you're running through a network that is not having full timing support or no timing support, that's just the packets coming through. And depending on the details of the buffer management in various equipment, small packets can actually get worse performance than if there's larger. So if you go for 1500 MTU or 1000, that could work much better than going for 64 bytes or something like that. The locket packet filtering, as I spoke about, or minimum filtering, that's a technique which already exists in partial timing support. But in order to use it, you need to adjust the parameters in a different way in order for it to work in the WAN environment. And so that's one of the key things that you need to address and start looking at. And then another thing that we add is something called multi-link, and I have additional slides on that too. And that is, rather than having one link providing timing, you can have multiple links going into a node. And if one of these are doing something, you can reduce the impact of that, and you are both able to detect problems, and you can smooth out variations also just by through and essentially averaging. So you reduce the weight of any of the links, etc. And it's a very helpful trick, which have not typically been the way you've done it with P2P, but that has proven to be a very useful property as well to use. When you're building a network in the WAN, you want redundancy for all the other purposes of just resilience of link paths, etc. But if allowing the use of multiple at the same time and fuse them together to give the time helps significantly as well. So it's another tool in the toolbox that we added to improve on things. So I mentioned before that we're now taking this into the standardization. So we started that in November, December 2023. And the current agenda, as you can see, it is supposed to be finished by 2025, which for those who follow the question 13 group means that we will have the final document for approval in the October meeting. And it is a lot of work to do this, especially as we are new to ITU and learning. But it's been very interesting, and we have good support from our colleagues in the group. So it's been both an interesting and fun experience. Now, one of the things I wanted to kind of touch on is we have a little situation where we talk about jamming. And this is a little bit of a sidetrack, but the interesting thing is we see this on many different areas. And when you're doing WAN, you see this. We have the first customer for this is having a lot of jamming issues. That was driving for them. And we now see it's close to ourselves. And it's interesting to note that conflicts trigger jamming even when you have low intensity conflicts. And it's also interesting to see that jamming is now being used as a defensive mechanism, so that you jam your home turf, the key locations in your own backyard, in order to safeguard them from, for instance, drones, etc. And telecom companies and other similar users will be indirectly affected by this. So that happened, for instance, to one of our customers. They all of a sudden a jammer was turned on, and that hit the whole town. The mobile network went offline after some time, after the holdovers, or they reduced their capacity, and they had to restore it through cabling in over the WAN, the timing. And the jammer, this was it 6-7 years now, and the jammer is still operating. We now have a situation where we have long-term jamming for these purposes. That is, when you have that on your own home turf, then the situation becomes quite different. So it's not always that we have access, even if we have free air. I talked a little bit of standardization. We do the question 13 is obviously where we do the ITUT, but I think there's a couple of other things that also bring up. We have IEEE P1952, where we work on resilient P&T. This is interesting because it's a multi-sector thing. We work with telecom, power grid, broadcast, and many other P&T users. There's also a ICAP steering committee set up, and this is interesting because it brings in a lot of people that have not spoken so much with each other, and I think that's the situation we're moving to. We now need to think not sector by sector but together. So I think it's an interesting effort, and I personally spent quite a bit of time on that one. I also noticed the European Commission spent money to do a project called Starlight, which is standardization of Galileo timing receivers. And we now have a good standard for that. We didn't have that before. So that's an interesting development too. That kind of fits the larger part. And another thing just to give you a little different angle on this. In Sweden, we're a Swedish company, we live in Sweden. So here the regulator, they collect a little bit of the operator's money. They match that one-to-one. They invest this in natural infrastructure. That's bunkers. It can be fiber projects. It can be backup powers. But it also includes building the, the kind of cesium-based clocks or time nodes, as they called, as operated by NetNode. This exists on 6 different locations. And these locations is also where you exchange traffic between operators. So this makes it very easy for an operator to get redundant timing in a very dispersed pattern. It's it also importantly in a neutral fashion. And this is kind of an enabler thing that helps in doing this, because an operator can now just plan to tap these different locations and spread throughout their network as they seem fit, but they do not need to invest in their own cesium setups, but they can focus on their networks, which is what they want to focus on. And this, I think, this is an interesting sample of how it supports development but do not enforce it. However, all 5G licensees in Sweden, they need to be independent to the loss of resources from outside the borders of Sweden. So anything outside the Kingdom of Sweden needs to be something you can lose. Now, so they cannot depend on a data center or other things. There can be such resources, but they need to be able to survive and operate sufficiently efficient. Turns out this also includes GNSS. So they need to have a way of being independent of timing. Considering the existence of these clock sources, it pushes them towards it, but it doesn't explicitly say that they need to use it. It kind of gives away itself. This is a solution and approach that have been many people are looking at. So it's kind of background material, which I think is interesting to look at. But let me now go back to, okay, so when we go into the WAN, what are the challenges we have? Well, the obvious one, first of all, jitter. We already see that before, and the jitter, the variation in the delay that comes from cross traffic, which is something you will see when you're in a network that do not support timing. Because if you have networks that, if you go through, let's say, a switch that has P2P full timing support, that is, it's either a boundary clock or a transparent clock. You, one way or another, compensate for the delay of traffic going through that node. In the boundary clock, you simply remove it because you regenerate the signal, you isolate it to the ports, and it's fine. In transparent clock, you compensate for the actual delay. Both methods have their benefits and drawbacks. It's good to have good solutions, but when you're in a node that to have no such thing, your packets, your UDP IP packets will experience the buffer delays, and it will vary depending on how the traffic is happening, and it will change completely over time. So that's where the lucky packet filtering or the minimum filtering comes in. But for that to start to do any useful action, you need to send a lot of packets to build in order to remove that noise. So the first part is increase the number of packets per second. The second thing that you will hit you hard is asymmetries. There's no guarantee you have forward and backward path of any exchange, taking the same route with the same delays. There are static asymmetries because you take different paths. There's there can be dynamic asymmetries due to, for instance, the jitter. If we manage to reduce the jitter, that reduces down. But then the third part comes in, which is also a dynamic property, reroutes. If we reroute um, one of the directions, we will have a different delay. We will have a different asymmetry. So it's not sufficient to discover an asymmetry and compensate for it. You need to discover when things are rerouted. It could be a protection fault, it could be a routing table change, whatever the reason is. You need to discover that situation and learn the new situation for asymmetry. So when you compensate for it, you are able to get back into decent numbers. So just doing one of these will not be sufficient. You need to do the full suite of these to address the different challenges we see. And we, I think we already covered. But here we have again a slide that kind of reiterates the point. You need to increase the packet rate, so you do your minimum filtering on a large number of these packets. So you can choose the packet that had the best transition through. And if you're not used to the minimum filtering, what you do is you timestamp the packet as it goes out. As it comes in, you timestamp it. You look on the difference. And when you do this for a number of packets, you choose the one with the smallest difference because that had the least amount of added delay due to packet variations. And you say, this will be, for this time span, the one we used. And you do that in both directions. And that way you can filter out noise. If you do it for 2 packets, you get the one which is best of 2. If you do for 4, you start to remove even more noise, and the way you go up. And it's not uncommon you want to do thousands of packets that in order to remove a lot of noise. So you need to the mechanism is already there with partial timing support. But the parameterization of it is one of the key things that really makes it start to be able to do something useful for us. What we have chosen to do, which also I think is interesting, we have made, rather than doing, when you do PTP, for instance, you have the same exchange rate for these messages for all the links for the whole region area. We do it per link. You can adapt this per link to address the local challenges. And so you don't need to load links unnecessarily, but you can improve situations on the links that need it. I think that have also proven very useful. We can focus on the key parts and improve the situation there. I also talked about the sync packet size. This is also proven to be a very useful thing. And the diff serve value, depending on, it's not always the best diff serve quality gives you the best timing property. So it can actually be interesting to try different diff serve settings. So being able to do that, we are able to find the most optimum for this particular link. And as we do the minimum filtering, we also with adjustable filter bands, etc., we do the multipath routing that I talked about. All these combine to push things in this direction. Then as we come, I talked about the rerouting, and the critical thing there is you when the situation for a link changes, you need to learn that you now have a situation where your asymmetry compensation no longer is valid. And there are a number of things you can do. We'll list a number of here's just to illustrate things. You can, for instance, detect a sudden change in round trip time. And the round trip time is you look on the difference between the timestamps, as I spoke about before, in both directions. You sum these together, you get something called the round trip time. And that's actually one of the few values we can really trust here. And because the time difference between the nodes cancel out, any asymmetry cancel out, that number will be a fairly accurate estimate of the actual delays. And so this is a good value to look at. You could also look, for instance, on interruption of packets. So if you have timestamps, but also sequence numbers on this. So you can easily detect, oh, there's a number of these missing. While since we're pushing a lot of these packets down and only selecting a few, missing a few packets is not a problem. But it's a good indicator that something happened to the link. That can happen, for instance, when you do a reroute. Also, other things can change. It could be jitter, packet loss can change, etc. And there are a number of different characteristics can change that you can use an indicator. And also one of the things you can do when you're doing a multipath, that is, you have multiple links going to a node that you're using for timing at the same time. If one of them are changing, but not the others, we can actually, when we have three of them or more, we can say this link jumped this much. And so we can point out which is the offending one, and we can early take action. All these comes in to do this. And here we have illustrated this where we intentionally did a symmetry change or increased the delay in one direction. And you can see here how the produced PPS from this node has one spike only at the time of the failing part, and that was a slight miss in the software that we fix later. But it's still on a very much lower part than the milliseconds we jumped. So it illustrates really how well this can be managed if you do it well. And we managing these shifts and following them properly, you can keep the systems well within the parameters we need, even if you have millisecond jumps on the link. And this is something we actually see in actual networks. So it's not something taking out of the hat, but it's actually just a reality we need that we will live in the WAN when we don't have the timing support. So simply you detect it. If an exit link profile is used the known TE offset. Otherwise, recalculate the new and use that and compensate actively for it. This is a very important part, which is not in partial timing support. So that's new with the ePTS. Also, another aspect that we have the dynamic of symmetry. Detecting for asymmetry can change in the network because of the way it can change across the operations of the network. So just you need to the change detection. You need to be dynamic. You need to be um, you can you cannot have a static value that will fix it for everything. Some links are noisy, others are not, but it also changes. So you need to have thresholds that are dynamic and based on the variation of the actual link that you're operating from. That's turned out to be because otherwise you can miss things or you can overreact because if you're using the wrong uh, thresholds for detecting these shifts. This is also very important to do to when you create profiles and manage them. And depending on the noise level, these can be like 20 nano, micro, 10 micro. It really depends so much on the link. But it's another aspect of this in the dynamic. You need to really track these changes deeply. I talked on the multipath, but I think it's also good to kind of illustrate this. You could when you're doing traditionally you choose one path in your network to you have a source and you distribute it out and you do a spanning algorithm or something like that. However, one of the things you can do is you can realize, wait a minute, I have access to this source from different paths. So if you look here, we have 3 nodes that have, in this case, 2 inputs each available at the same time. So rather than choosing one of them, traditionally we would choose the shortest path only. But here we have the opportunity to actually say, wait a minute, I also get timing here from a slightly different path. And so let's use that. And now I can combine these and I can weigh them equally, for instance, in the simplest one. So I depend 50% on one, 50% on the other, or I could do a more complex one where I let the stability that I actually get on them steer the weighing. That you can do it in a classical ensemble mechanism, or you can do it a very straight. Even the straight one is actually significantly improving the situation because any unique variations on either of these links will be halved or reduced by the number of 1 over n inputs I have. So it's actually a very low-hanging fruit, but it creates a little bit of difficulty because you cannot use exactly the same algorithm we used before to select so you need to be a little more careful, and we made some changes here in order to enable this. Yes, of course, you need to do your routing loop prevention as always. That is bare minimum for any synchronization system because that would be completely terrible if you do. So that's an obvious given. But this has proven to be a useful tool in the toolbox. Um, when you transport time over non-P2P enabled networks, you can. It's actually a situation in the WAN. We have a situation where we could either operate over a fixed part of our own network, but here we also see, for instance, could be lease capacity. Sometimes to reach a tower, you lease capacity even from your competitors, etc. They're not necessarily likely to provide you the best links, etc. But so that's another thing. In reality, it's rented a lot of capacity from each other to just solve problems. It's quite promiscuous in some degrees, but it's by doing this, so you jump over shorter paths between nodes that do know the time, how to do the timing. You can then jump over different segments they will have different properties, but you are able to kind of build an overlay over those different parts of segments. Part of this could also be microwave links, for instance. So there is a, a wide range of different underlying network properties that could be there. So, but by not being tied directly to these physical details, you can actually bridge them and mend them together. And I think that's also an interesting thing, because that enables many different solutions. Here, for instance, we illustrated with core, transport, and access, but that could look differently depending on the details of the network. To further illustrate this, we built a network where we have ePTS time nodes distributed not densely, but might look dense in this case. But here we jump from we have a source, we provide we get timing over P2P over to the ePTS node. This then distributes over to intermediate nodes that could provide multiple paths through the network out to, and this is typically more a deeper network than this, but this is enough to start to illustrate how there can be several other paths in the network. We can do several paths on that overlay. This is what you typically see in a mobile operator network, for instance. And many of these properties you really need this, you adapt it to each of the local situations. Again, the same message on how the multipath is actually allowing us to utilize these different paths. And then what we do also that we think it's important, we bring the data up to a centralized system to see what's happening there and get an overview. Locally, you don't really get the full overview of what's happening in the network. And this brings us into what we think of the kind of central intelligence, or the director, which is really you bring the data up, you observe what's happening, you analyze this, and you try to do proactive optimization. This have turned out for one operator, for instance, here. They just ended up using this as a way to analyze how the network was performing, and that it will also provide a timing was fantastic additional benefit. So it was interesting how it became a tool to understand their network. And when they was very generous with us, and we said, give us your worst link. And they gave us our worst link far out in the woods. And then we were able to find even what's wrong with the links to that location. And when I've been focusing on a little bit on how we do things locally, but then as you back out and collect data for the full network, you can start to do optimization of the network with that central knowledge. You can piece together a better total picture than you can do in either of the local nodes. And this way, you can fine tune the network, the asymmetry compensations, etc., in order to get an even better performance. The nodes can operate themselves without this. They do all the basic things, but you are able, whenever you can maintain this central ability, it allows you to wash out a little more of the uncertainty and give you better margins to ensure that you reach the full potential. And here this comes back to, you can do the route and linked optimizations. You can look on the PDV, you can assess the filtering, the timestamp select, all that. You can look on the symmetries and look on the spread. You can do global auto calibration, so you really bring in the full network. That you can also look on the change detection, that the profile management, and improve that. Then you come to observing other characteristics like diurnal variations. That can actually be that can be a little bit hard to do on the local scope, but as you look on the data and the data you get over time, you can see these trends, and you can learn how to fine tune for better performance with that. Here a little bit. This is actually slightly outdated because we had a couple of meetings more, but it's ongoing work in with standardization. And we had a meeting in March in Geneva. We just had an e-meeting last week, and we're preparing the Paris meeting in June. And there's a lot of work. We have a few of our fellow colleagues from Question 13 with us, I think. Um, and but this is ongoing. And in addition to this, I wanted to kind of bring you over to a little fun thing we've been toying around with. So we thought we wanted to check what you can do, because previously we've done this with FPGAs and we have full ability to do things. What if we did this with much simpler hardware? Let's say we take a couple of Raspberry Pis. So we did a proof of concept testing in our lab just for fun, and just to see how much can we use, etc. And so here we call our product SynPi, but here we call it for fun SynPi. And we took standard Raspberry Pis, Raspberry Pi 5s, and we did the packet generation and parsing. We set up timestamping captures that was sent using the normal Linux timestamping functionality, just using what the hardware is able to do there, and operating and grabbing that through the Linux system. We steered things with the Linux clock system. We did timestamping. We also did the AES encryption decryption of packets using OpenSSL, hardware accelerated on Raspberry Pi 5. And the interesting things, we were able to make these links compatible with the NetInsight Syntyne nodes. So we were able to replicate it. And so this was the setup we did, the setup we used existing nodes, and then we tossed in our test setup, Raspberry Pis, and we chose 4,000 packets per second. The synths, they are FPGA based, etc. Here we're using standard hardware and just a little bit of code adapted to the situation. So it's on the same network switch, short cables, no other network traffic. So it's a little bit of a golden case, but this is a proof of concept just to see what's possible to do. And here we have, we see that we have really down to tens of nanos of seconds over such a link. And it's actually quite promising results for something we didn't really do. And it's important to remember that this is a very controlled environment, short cables, no other network traffic. But it gives that at the same time, it gives an indication that how good could such a setup be. But so it's a little bit for fun. We're toying around with seeing if maybe we open source this or not. We haven't decided. But it's illustration that the concept works and the implementation works. So I thought I would toss in this to show you, and hopefully that will be some good food for thought on what you can do with timing on even these platforms and with essentially existing tools. So with that, I conclude the presentation. I'm open for questions.
Magnus, good afternoon. I have a question for you. In one slide, you mentioned that you can correct dynamical time error up to one microsecond. That is a value, that is a limitation, or the dynamic time error for this kind of
No,
networks
it, it,
fits 1 second is the maximum.
it's more an illustration of, so it's not a limitation in any sense, but it's an illustration of it. What we that is actually on how it was an illustration of how large variation of the detection mission, because if you have high jitter, a noisy channel, you need to have a threshold that is large enough so you do not do false detection just from the noise. So that is it's it would just to illustrate just how large such a limit can sometimes have to be, whereas in other cases it was down to 20 nano. So and 20 nano, then you have very low noise, and by in knowing the variations can be that wide, you also learn that you need to adapt to the situation of the link. And we're even pointing out you need to follow the situation, because over the day, over the week, the behavior of the link can change. So this is driven by the traffic. So if you're sitting in the part of the network which, for instance, see a lot of residential traffic, when people are working or when people come home, you see the traffic load change, the variation change, and you need to track that if you want to be able to detect when things happen. So this is an illustration just of how wide range that can be.
Let me ask you another question. I think it's related with your answer. In an IP network, it's very common to have multi paths. So and the routing decision when there is a routing decision, but upon a failure or at any moment the route can change, and there are potential routes to get to the other side. How are you in advance to try to learning these patterns and to adopt your correction in advance, or you just do that, or this the protocol also applies this correction upon starting a file?
The answer is it needs to do both. So what you can see is if you now have a situation that you jump over a suitably small part of a network, of a large network, the number of different paths you can take is usually fairly bounded. Then you can remember previous calibration points, and that might be useful. But it might also not be useful because it can be under different traffic load conditions, etc. But you can also have a situation where you have a reroute over a link you never seen, and you need to handle that. So there's no given answer that will always be true. This is why you need to detect the change. And now, if you have a situation where you have two nodes that have a well-calibrated, well-understood time, but you now have an asymmetry which is uncompensated because the new situation came up, then you can calibrate the link and use that calibration to compensate the link. You can do the measurement, do the compensation, and all of a sudden that link is compensated again. And so what you need to do is when you see such a change, the change detection is really important. That's why I spent time on it. You need to see the change, evaluate. Have I seen this before? Is any of those existing profiles useful? If not, I need to create one. And you need to do this directly, instantly in the node. So that's each node needs to be able to do this for all its links. It needs to make that decision when it happens. Being in holdover when this happens for a second or 10 seconds even is not a problem. Even simple oscillators have really good performance in that space. So, but you need to make the decision because you don't want to stay in holdover for very long. Because and usually you don't need it. You can do it in a fraction of a second if you do this properly. And you just need to make the decision what is the right action using existing profile and you apply that, or build a new profile and apply that. And typically we recommend having multiple paths to a node, and in that case you maintain a good stable phase anyway, and you can use that to even be more sure of the situation than if you would just be in holdover. So there's tracking these changes are extremely important to survive, because otherwise if you do not track it and use an old compensation on a link which is way different, let's say that you get 1 millisecond of additional delay. That additional delay in that direction will give you 500 microseconds of timing error instantly, bang. And that will hurt whatever you're doing for most applications. So pushing it in order to keep it in that sub-microsecond region, these are the tricks you need to do to survive it and maintain a good, healthy situation. Make sense?
Makes sense. Thank you. It was really good presentation.
Thank you. Further questions?
I just wanted to say thank you for the good presentation.
Thank you.
It was easy to follow and it made a lot of sense.
Thank you. I appreciate that.
So, Magnus, if you recall, I had some exchange with you about availability zone. Do you remember? And some ITU T question 13, study group 15.
Yeah.
They were talking about availability zone as if it is a data center, and I wanted to get your input on this. Is the availability zone a data center?
Can be. When we done this, our main focus have been to the mobile network use, and this have kind of been the main driver for us. But this is a generic technology you could apply to many different things. And you can hand time over to data centers. You can hand time from data centers further out. So it can certainly be data centers. We have not aimed for the data center market and optimized for it, but we're open to look at the different opportunities and see what fits, what's useful, etc. So we're open for these discussions.
So how you define how your company define availability zone?
We it's not a term we use a lot, actually. So you put me a little bit on the spot, because that's not at least something I use a lot in my work.
Okay.
So
that's sort of an amorphous concept, right? Because something's available, and therefore in the availability zone until it's not. And whether that's in the same rack or in potentially another data center, but a link gets clipped.
yeah.
Magnus, great presentation. I did have a quick question. I couldn't tell from the slides. Are you using with the Raspberry Pi? Some of them have EDP support, and they do it at different levels. I think it's only the CM4, if I recall correctly, that actually has it in the Ethernet Mac. And then at least with the Raspberry Pi 5, they do it further up, I think, in the RP1 or whatever it's called. But were you using any of those features, or was this just 100% stock Linux doing software-based PDP?
That's stock Linux on a Raspberry Pi 5. And this is something we just did the other week in our lab, so I kind of shared it for fun. But it's the interesting part is really what's available to do with off-the-shelf components and off-the-shelf software support. I think that's the interesting part here. We've seen people, P2P timing, it's specific, blah, 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 but actually just the general time stamping support that we can get from such a hardware is actually really good. This is just using the general available. We send IP packets out, we get the time stamping, we use that. I think that's an interesting part. That was our focus. It's feasible.
100%. If you're interested in this more, I've had students working on this for several semesters. So if you want to touch base, feel free. I literally have one of these sitting on my desk right now, hooked up to an atomic clock.
That would be fun. Yes.
All right. Any more questions before we adjourn?
Are there any contexts where they look at actually doing sort of mesh-based distribution for cases where GNSS is denied in some parts of the cellular network, but not others, but where you may not have fiber to the individual cell site?
We have such. We built it and tested it from. I mean, for instance, it's no secret we have a big customer in Turkey that have that situation. And they use this to move time around in Turkey to overcome these situations. We have other operators where they, for instance, do not have roof access, so they can't get GNSS in there. And it's a way to solve that solution. In the US, for instance, you have situations where you can need to pay multiple thousands of dollars a month just for a cable going up to the roof, because typically that means you have a transmitter there and you're making money out of it. And that's not the same budget for timing. Timing is not getting the same good money that you will get from let's say a mobile transmitter.
Very interesting. I'd be curious to follow up to maybe later offline if you have any statistics, for example, of when you're seeing jamming, what are the characteristics, which frequencies are they doing at, for example, if you're ever detecting really more complex things like spoofing, and whether they do it cross spectrum, cross satellite constellation, or is it just like L1 GPS?
Yeah. There are people who do spend quality time on doing things like that. For instance, there was an EU project called Strike 3, which did exactly that. There is public information available that gives give statistics on how many detections they made. There are statistics of how many different, which type of situation it was, if it's jamming, spoofing, etc., or interference. And that was using many different locations. I saw the more detailed briefing that's not public of that. That was really interesting. There is other sources that look on that. Not all of them are open, unfortunately. And we don't keep statistics like that ourselves. That's not our main business. We make products and we try to solve the solution. But I agree, it's interesting because it's interesting facts. What I would recommend you to do is check with DHS or MITRE if they can provide you with some information on that, for instance.
Really appreciate it.
I might say that DHS is working on, they had an ongoing work under Presidential Directive 13905, which they spent to build resilient P&T, etc. There's a group of it. MITRE is then doing their part of that as hired in as per usual. And the work that was, I recommend you to go to the DHS CISA and you can find the publications there. That work is then continued in the IEEE P1952 and ongoing. And the P1952 standardization is due to be finalized at end of 2025. I think we will overshoot it a little bit, but in general, that's the direction. But I think that's a number of resources I recommend you to look at. The things that DHS provided through CISA is provide a number of different insights. I also recommend you to look at what comes out of the Volpe Institute, that's part of Department of Transport, that's also looking on this. There's also work with Department of Energy, look at Oak Ridge National Laboratory, for instance. So there are a bunch of sources. Go for them. If you don't find them, reach out, and I'll happily help you to locate most of them at least.
Thank you so much. Really appreciate it. And wonderful presentation. It was great to hear about this.
Thank you. There is also some resources at GPS.gov. Check both the USP&T Advisory Board as well as the CGSIC meetings. I held a presentation for CGSIC in September at the Baltimore meeting, for instance.
Thank you so much.
Happy to assist.
All right. So probably we should adjourn now, and we'll see everyone in 2 weeks with a presentation by our very own role about the Furgo's Atomicron's some updates, and yeah. All good? Yeah.
And if anybody of you come to the WSTS conference next week, I'll be there.
Wonderful. All right. Bye, everyone.
Take care.
Great day, everyone.